All right. This is the last part of this lecture series, is working with non-OpenAI Gym environments and how to create, how to implement this agent environment loop from scratch to understand actually what is being happened and what to expect in the back end of those API function calls that you did at OpenAI. So the first non-gym game that you're gonna see here is a 2D text-based game, which is essentially a 2x3 grid, right? It has 1 to 6 states, where 2 states are terminal states, whether this is a goal state or a whole state. So if a player or an agent moves into any one of the terminal states, the game is over. And 4 non-terminal states, say the first one, second, fourth, fifth. So these are the 4 non-terminal states. So if you are in a non-terminal states, the reward is 0. If it is a whole state, you get a minus 100 reward, which is essentially a penalty. Plus 100 if you end up being in a goal state. So we'll define a class goal versus whole underscore v0, and since this is actually I'm defining it in a Jupyter notebook, so multiple cells, I'm going to use this class dot member method. We'll define a function and then we set it as a member function using this weird syntax, but I believe this should be okay. I mean, ideally, actually, if you're writing a Python script, a class, this you put that as a member function. All right, so the very first function, member function, that we will define it as a initialize reward table. And you can see actually based on the rules of the game that you saw in the previous slide, being in a whole state is 100, whole is negative 100, goal is 100, and everywhere else is 0. And you just prepare a reward table for that. I mean, it's a 2x3, right? 2x3 dimensional number of zeros that you pass, and then 1 to this position you set to 100, 4 to this position is set to negative 100. So that's the reward table that you will be working with. Then this is very important, since this is the action space. Any one of these action that you can take, 0, 1, 2, 3, it can be going left, going down. This will be interpreted as going right. This is going up. And these are the observation spaces. Is pretty much the state space, 0 to 5, right? So these are state space. 2 of them, 2 and 5, are terminal states, and 0, 1, 3, 4 are the non-terminal states. And the transition table is if you are in a particular state and if you go right, which state. So that means you want the agent to know the structure of the environment, right? I mean, so what the environment looks like, right? We don't want it to explore. I mean, this is nothing intelligent. This is actually defining the structure of the environment, right? So if you are in state 0 and if you go down, you will end up being in. So what is the transition which is defined by that action, right? So if you're in 0, 0, if you go left, you will end up being in left. 0, 1, so from 0 you take down action, then you end up being in state 3, and so on and so forth. So you can see actually this is, and also from, if you're at a goal state, if you take another action, you will be in goal state, because that is the game over. All right, so this is the transition table. The reset method that you saw in OpenAI Gym. So here we are resetting on a initialize the starting position, right? So self.state, the current state, it can be randomized, or you can pass it a specific value that is that you can pass through the reset method. So initialize here, these are number of actions that you can take, total number of states that you have. So this is actually, we're trying to put everything into, organize the Q table, right? So this is the Q table. The dimension of the Q table has to be state versus action, right? And we call the init transition table and init reward table to populate that those tables. Those becomes the member variables to the class. This is the discount factor, close to 1, right? It's 0.9. So that means we're not, myopic, right? The agent, we want to see actually what are the future rewards that it might gain. This is the exploration rate. We set it to 90%. Decay 99.99, meaning actually we want a smooth decay rather than sharp decay of exploration. So we want to let the agent play or explore randomly to see actually possible options available. And also actually we still want to, during training, we still want 0.1, so 10% exploration at the end still. So this is the minimum threshold of exploration rate. We call the reset method to initialize at a start state. And is explore is a flag that we set. So at the beginning it has to explore. So detecting whether, you remember that actually environment, the OpenAI Gym's step function returns a flag called terminated, all right, true or false. So you need to detect whether you're at a winning state. So if the self.state is 2, then you're at a winning state. Step function, we need to define that. So we pass an action. So based on the transition table that we defined before, you see actually what is going to be the next state. And if it is either 2 or 5, these are the 2 terminal state, you set the flag to be true. Terminated flag, or the done flag here, is true. You collect the reward based from the reward table, and you update your next state, right? And you return these values, right? So right now actually this step function returns these 3 things, unlike the 2 additional things, which is in this particular game very rudimentary. We didn't need to truncate the length of the episode and so on and so forth. Act. So this tells you actually the policy, right? So based on the exploration rate, this is the exploration rate. So we want to explore more. So here we did something interesting. So based on available action space, right? So say for example, if you're in the top left corner, going further left is meaningless, right? So in that case actually we want to offer what are the available actions. We call them valid actions, right? So and we will choose from the set of valid actions rather than all the available actions. So here we are not choosing from all the 4 action space. We are choosing from the valid action space. You might see actually this is actually a very simple thing that we did, and we played with the transition table that we have. So if it is the same state, that we will discard them from the action space. So to reduce the number of to limit the action space in a valid order, so that the agent can learn or explore quickly. All right, so this is exploration. So if we're not exploring, so we'll leverage the Q table, right? And we take the action based on the Q table. And update Q table, this is actually a dynamic programming based Bellman Equation solution that you can see here. So we collect the reward self dot gamma times all the best Q value based on the actions that we take, and we update that Q value to a specific position in the Q table. We want exploration rate to go down. So unless you're testing it, right? So if you're testing it, definitely we want to explore. We don't want to explore. So this is actually a very specific hard case. Other than that, actually we want to decay the epsilon using the decay rate that we set. These are a couple of print. And also this is not meant for Jupyter Notebook execution. So I hope that actually you're going to be running this on a terminal so that you can. So I've used the colored. It's a term color library that you'll see is to show the G character or H character in a different color, so that it looks nice. This is a text-based environment, so you get to see that. This prints the key world. The goal versus whole world, the version 0 world, which is a 2x3 as a grid format, so that you can see actually what the agent is doing every state. Kind of a visual. So in this is just an example. This is a text-based game, so you can understand actually what are where you need to put some time in first drawing the board, and drawing the state, and where you'd like to put the scores in the current state, or if it is a say grid and you want the agent to move left or right or down or up, so the position of the agent. So these are, you need to invest some time on architecting this particular environment, right? So you can understand how to structure your environment or the reinforcement learning problem setup this way. This is a printing the Q table, and also it prints at that moment what is the epsilon rate, the current exploration rate. This is actually saving as a joblib file the current Q table, and also besides several other values as well. So we're saving a good number of values. Load world is going to load all these variables stored in a joblib file, so that we can evaluate or test without training, right? So print episode is going to print the entire episode. It calls the print methods. Print status is going to print the world. And you will see, these are a couple of visualization functions that we see here. So these are the two flag that we're going to use. So the first is do training equals true, do test equals false, meaning that actually that the following script is going to train the model. And once the training is done, definitely you switch the values. So you don't want to train, so set it to false. This is to true, to see what is how your agent is going to behave. Do training. So this is the training part. So we let 2000 maximum wins, so that you want the agent to explore and exploit in a way so that it sees 2000 times be in a goal state, right? So this is the delay. Since this is training, I mean, we don't want to have a lagged display, right? To visualize, similar to the human render mode that I mean, RGB array or no render mode set in OpenAI Gym. So, and also you want to run that many episodes. You create the world, you reset that, and while in a, this is actually within an episode, this is done. So we call the act method to get an action. So based on the exploration rate, is going to return an action, and we call the step function. We pass the action, so it will update the environment. You get a new state, you collect the reward. So all these three values are going to be returned, and you update your Q table based on the strategy. At this point, the strategy was dynamic programming, and you print the status. You call this state your new current state. If it is done, meaning that game over. If you are fell into the hole, check if it is a winning state. If it is a winning state, you increment the win, and you accrue the scores. And if it is, I mean, if you pass the number of max wins that you set, which is 2000, you break, which is, I mean, enough training or enough learning the agent at that point. And since this one episode is done, at the end you decay the exploration rate, right? So this function is going to take care of that. All right. So, and you, at the end of training, you save the Q table, and just to give you, since I didn't want to learn, I mean, how I didn't want to execute that in the Jupyter notebook. Instead, actually, I encourage you to, I mean, run the scripts on a terminal. So this is actually the terminal demonstration of the training. So as you see here, with no delay, this is the at the top left corner. This is the Q, the environment is being displayed, and the underscore that you see, this is the agent's current position. Sometimes it gets to G, sometimes it gets to H, and here, down here, you can see this is the Q table that we're talking about. So it has 6 states from 0, 1, 2, and we have 4 actions that we take, that we'll take from. So at that moment, actually, this is at a particular state. So at a particular state, you can see this, which particular states. If you're in state 0, what is the best possible actions that you can take, which is here. Probably this is the first column detects is the first action, which is going left. This is going down, this is going right, and this is going up. You can see that actually, if you're in state 0, the Q learner, based on the dynamic programming that solves the Bellman equation, it tells that going right is the best solution. So if it is, if you're in state 1, which is just the next state, is going right is the next, the best position, because going right, you'll end up being in goal state. So you can see actually that this is the final converged Q table, right? And which is, at some point, actually, you will see actually at the beginning, your Q table will be changed after every update call. At some point, actually, you might see that actually the Q table is not updating anymore. Maybe at that point you can call it that the Q table is converged. Very similar to the notion that you learned in supervised learning, the stochastic gradient descent. We look for convergence. So this is actually what happens. All right. So during testing, you can see the similar function call. So you take an action. So here you see that we begin from a very random start state, right? So, and we're starting from a non-terminal state, so to make good sense, right? So and then we act, we act and we registered that action through the step function, and we update the Q table. We don't want to update the Q table. I don't know actually why I did that, but again, it don't have any effect. I think this is a redundant function call. I copied and paste. So if it is a win state and so on and so forth, and also actually since this is a do test is set to true, you understand that the exploration rate is set to 0. And this is actually what it will look like during testing, and we added a delay so that you understand every single step. So initial state, then this one, and it follows the Q table to which is defined in the policy. Though your Q table is going to be translated immediately with the policy of the agent. If it is you see that the epsilon was set to 0, so that it's easy and follows that, and which is pretty good. So it is not falling into the hole. It's no matter where the agent starts, it ends up being in the goal state. All right, so this is one of the game, which is a very simple text-based game. Just quickly going through another variations of the goal and whole state is this one. This is a 4x4 version of the environment that you just saw. It has 16 states, so 0, 1, 2, 3, 4, 5 up until this is 15, and it has a bunch of 3 holes and 1 goal. So similar to the 2x3 grid that you saw. So 4 terminal states, including 1 hole and 3 goals, and 12 non-terminal states. The reward rubric is the same, and we're defining the class goal versus whole v1, and this is the reward table structure. So if you're in state 6, you will get -100. So whenever you're in these states, you will get -100 reward. If you're in goal state, you get +100. Everywhere else is 0. So you define a 4x4 matrix, and you set the goal and whole reward values. And transition table is very similar to what we did here, did in the last time for a 2x3 grid. So right now actually we have 4x4. So so for the sake of convenience, actually I enumerated left, down, right, and up actions to be 0, 1, 2, 3, so that it's easy and more easy to follow transitions. And you can see actually this is a little exhaustive, but again you see actually that OpenAI Gym, somebody defined them, right? So define those transitions from one state to the other based on the action. But here in this particular case, we have to do that manually or on our own. Reset, similar to that. Passing a starting state, you can randomize that from the color. Init function, so we have 4 actions. We still have the 4 actions. We have 16 states. We define the Q table. We initialize it to all zeros. We call the init transition table, init reward table. This is the discount factor, not myopic again. epsilon decay and epsilon minimum threshold of the exploration rate we have discussed, very similar to the previous one. We call the reset method and exploration to be true. If it is a win state, which is only one state that you will find in the grid, which is state 10. Step function, given an action, you'd like to see actually, you'd like to return the new state that you will be at based on the transition table. And these are the terminal states, right? So 6, 9, and 15 are the hold states, and 10 is the goal state. So this is going to be the done, right? So, and the reward table, by consulting the reward table, you collect the reward. So, and also this is going to be your new state. So you return these 3 numbers, and the act method, based on the policy, and also exploration rate. So we take only valid actions, right? So this is the random selection of the valid actions that we can take being in a particular state. Or so this is based on the exploration distribution, exploration rate. If we are not exploring, we are exploiting from the Q table that we have learned so far. So, and this is going to happen. Say at the beginning, we're 90% exploring, 10% exploiting. So for following that distribution, which is set here, we will explore 10% of the time from the Q table. The Q table update is the similar from the last time that we saw. This is based on the dynamic programming, solving the Bellman equation. So the Q value is becoming that. So this is the epsilon decay, exploration rate decay that we saw. If you are testing, epsilon is going to retain to 0. We don't want to explore during testing. On the other hand, if it is training, then we will decay by a decay factor that we set, which is probably 99.99. This is for print purpose. You see, actually, you can imagine that actually that the grid right now has expanded by 4x4. How many spaces, how many bars, so the position. So every single state will have a position within the grid. So it returns the positions as a tuple of where that character, the G or H character should be, or whether that's going to be a space character if it is not a terminal state. So this took a lot of time from me. When I was defining this, just take good care. Inspect this. I know actually that it can be improved to have the same printouts of the states, every single step. But again, it was quick for me at that point. So this is a 17 character, so every 17 character, so this is gonna print out a single row of the grid. So this is the first row, second row, third row, so we can pass that, and based on the position, based on your state, he's gonna use the term color and so on and so forth to print out that cell. And this is this is called, so that particular row row of that environment is called here. So this is actually, so we print the first row, then we put some dash, and then for the remaining 3 rows, and then this is the final dash counts, and this is only for printer. And you can now understand gauge that actually underlying mechanism. So once, if the environment is not given to you, you need to design that environment, visualization, everything yourself. So just to give you an idea and heads up, then actually that, yeah, don't skip that. You have to, if you'd like to do a visualization, I mean, visualization is not important, but if you'd like to do visualizations and to understand and also debug the code very efficiently, I mean, you may want to, and also demonstrate in front of you that, yeah, look out world, this is what I did. All right, so this is the print Q table, which is very similar to the last time. We print the Q table as well as the current exploration rate. This is saving the Q table along besides other parameters of the learning environment. This is the loading from the joblib saved file. This is printing the episode, very similar to the last one, and print status. So now the big time. So do the training similar. So right now actually I reduced it from 2000 to 100 because it took time, a lot of time, but you can, and also actually you can change the dynamic programming version with the temporal difference learning to have it have a faster Q-table updates, so that you can have, and we can let your agent learn by being in the goal state 2000 or 10,000 of time. And this matters. I mean, if you'd like to make your agent learn more and more, I mean, and also get the shortcuts that you think that you'd miss by playing this. Very similar to the last time, nothing changed, because actually we defined some API, I mean some functions, which is very similar to the OpenAI Gym's functionality. So we act by calling that act function, we get an action, and we pass that action to the step function, and we see actually what are the next steps, and we update the Q table using the db Q table update routine, and everything else falls accordingly, right? So this is a 4x4 grid training GIF that I mean the demonstrations that I expect that you don't run it here in Jupyter Notebook. And here on the left, I mean bottom left corner, this is the Q table, right? So this is, we have 16 states and we have 4 columns, 4 actions. So the first column is going left, this is going down, going right, and this is going up. And you can see actually that if you're in state 0, I mean, this is going down is beneficial because your goal is in south, right? So your Q table, although actually we could do better. I mean, I don't know, actually I set the number of wins to be 100. So if you increase the number of max wins, you might see maybe it will converge a little differently. But I mean, and at some point maybe if you train it quite enough, you might see that the Q table is not changing much, right? So during testing, we follow the same convention, although actually I don't know actually why I call the update. We don't update during the testing iteration, although actually I called it. You will see actually that the Q table is not gonna change during that update call. So during update, I mean during the testing, you might say I put a D lag, and you can see that any random start location of the agent, it will find a way by consulting that Q table, because at that point, and the actions that you will see here based on the table, it will find a way to get to the goal state. But it could do better. I don't know actually whether it's comprehensive. You can try starting from any different locations. It should, by consulting this Q table, it will get to the goal state quite nicely. Let's see. All right. Yeah. So I guess that's pretty much it. Thank you for your attention.